Hello everyone and welcome back. I'm Mahnoor and today we will be going forth with some conceptual questions pertaining to kinematics. Now so far in the first lecture we went over some fundamental concepts when it comes to the entire topic of kinematics. There you were introduced with some basic definitions of distance, displacement, speed, velocity, acceleration, and then finally average speed, right? Now up to this point these might seem like just definitions that you just have to memorize, but especially in AS level physics it's really important that we know how can we apply them to practice questions. Sure, I could have just directly shown you some past paper questions and then show you how you can use your tricks over there, but it's more important that we understand them conceptually first before we even dive into those past paper style of questions. So we'll take the simplest cases first and then we'll build into it some complexity as we go forwards. Let's take the example of Tufi standing right here, who's ready to move from this starting position that I've marked with a dotted line. Suppose Tufi here moves 1,000 meters forward and then moves about 200 meters backwards. So perhaps Tufi lands somewhere right here. Now our first question is this. And suppose there are multiple parts to this question. The first part asks us, what is the distance covered by Tufi in this case? Well, the distance we do know is the length of the path covered, right? If I were to highlight that path in Tufi's case, it would just be the 1,000 meters covered forwards plus the 200 meters covered backwards, right? So we have to basically account for both distances covered individually by adding them together. So it would just be 1,000 plus 200 gives you 1,200 meters. Now comes the next part. What would the displacement be? Now the displacement wasn't as straightforward as the length of the path, if you recall. It's more specifically the length of the shortest path covered by the moving object, in this case Tufi. To know what this shortest path is, it's just a matter of identifying what's your starting point and what's your ending point. And now it's just a matter of drawing an arrow from your starting position towards the ending position. So it's this red arrow that represents displacement, and I'll mark it with the letter S. Now, in terms of the value or expression of displacement, notice how it doesn't really account for both 1,000 and 200. Rather, it accounts for the remaining distance once you remove the 200 meters covered backwards. In that case, displacement is merely 1,000 minus 200, which gives you 800 meters. Now, if I wanted to, I could have left my answer right here. But do you notice a problem over here? The problem is that we remind ourselves that displacement is actually a vector quantity. So a magnitude clearly isn't enough. You need to express a direction as well. So instead of just saying 800 meters, you could qualify this by saying it's 800 meters towards the right. If you want to be a bit more technical, you could say towards the east or any other specifying direction. The point is that any mention of direction is absolutely necessary. Great. Now let's follow this up with two other points or two other parts. What would the speed of Tufi be? Well, speed is just distance covered per unit time, right? Suppose in this scenario, the time that Tufi takes to go 1,000 meters forwards and 200 meters backward is about, let's say, 100 seconds. In that case, speed can be just directly evaluated as 1,200 divided by 100 gives you precisely 12 meters per second. Now, would you expect would you expect velocity to be the same? Now we remind ourselves that velocity is the rate of change of displacement, meaning it's displacement per unit time. We might have expected the same answer if distance and displacement had been equal, but clearly they're very different. And so we'll expect our value of velocity to be different as well. In fact, here it will be 800 divided by 100. And so we'll get 8 meters per second. So this is just one sort of a scenario where distance and displacement just so happen to be different, all because of the way the path of the moving object is arranged. Now let's look at the next question. Now the next question is related to our trustee, Dr. Sal, who's ready to embark on a journey of multiple stops. Let's say those stops he wants to make are starting from point A, stopping momentarily at point B, and then landing right at point C. Suppose the distance that Dr. Sal covers from A to B is about, let's say, 800 meters, whereas the distance covered from B to C would be 400 meters. Suppose that the time that Dr. Sal takes traveling from A to B is about, let's say, 20 or 200 seconds, let's suppose, whereas going from B to C, the time taken is, let's say, 400 seconds. Now the question is, what would the average speed of Dr. Sal be? We know our expression for average speed, and we'll remind ourselves of it, that it's merely the total distance traveled divided by the total time taken. Specifically, I'll write here, total time taken. It's just a matter of looking at this motion of Dr. Sal and seeing that the total distance is merely adding up both the paths AB and BC. So it would be 800 plus 400. Whereas for total time, it would be the time taken from A to B and then plus time taken from B to C. So it would just be 200 plus 400. Now it's just a matter of simplifying things. So we get 1200 divided by 600 and you get 2 meters per second. Let's look at another journey that Dr. Sal is ready to take. This too having multiple stops. So here we have Dr. Sal starting his journey from point A, stopping momentarily at B, and then going towards point C. Suppose the distance from point A to point B is about 1000 meters, and then traveling from B to C, the distance is about 800 meters. But this time, suppose you're not given the time durations of each of these paths, but rather are told that Dr. Sal travels with a constant speed of 50 meters per second along the path AB, and then changes his speed to a new value of let's say 80 meters per second in the path BC, this too being a constant value of velocity. Now the question remains the same. What is the average speed now? Now you might be inclined to ignore the distances given and then only focus on the speeds given and do perhaps a literal averaging like this. This would actually be completely incorrect because you have to take into account the distances and their different time durations. So it's far better to approach this by using the definition itself, which is, as we know, the total distance traveled divided by the total time taken. The total distance is easy to compute. It would just be 1000 plus 800. But we don't know what the time durations for each of these paths are. But whatever those are, we know for a fact that they'd be different. So let's say the time taken to travel along the path AB is TAB, and the time taken to travel along the path BC would be TBC. Now the trick to compute both of these times is to remind ourselves that both of these paths AB and then BC are being traveled at values of constant velocity. And there's only but one formula that we can associate with for any object, in this case Dr. Sal, That's moving with constant velocity. That is the definition of velocity as the rate of change of distance divided by the time taken. So it's just a matter of rearranging this formula in making t the subject of the formula to figure out each of these values of time. TAB would be the distance AB divided by the velocity along the path AB. In our case, that would be 1000 divided by 50, and you get 20 seconds. Whereas for the path BC, it's the distance along the path BC divided by the velocity that Dr. Sal has along BC, or the speed to be a bit more precise. This time it would be 800 divided by 80, which would just be 10 seconds. So now it's just a matter of plugging these values into our above expression, and so we can find the average speed as 1800 divided by 20 plus 10. We get 1800 divided by 30, and your final answer should be 60 meters per second. Right? Now let's address another question. Let's depart away from Dr. Sal for now and visit Tufi once again. Now suppose Tufi is seated comfortably in his car, like so. That's Tufi right there. And suppose he's on his way to work. And suppose he has an initial velocity of about 10 meters per second towards the right. Suppose he continues to move towards the right along the same direction in a straight line, and suppose he lands somewhere over here. And let's add to this by saying that suppose he's speeding up. Suppose he sped up with a final velocity of 50 meters per second. And let's suppose that Tufi takes a time duration of about, let's say, 40 seconds to do so. Then the question is that if we want to quantify this change in velocity, we know we use the concept of acceleration. So what would that value of acceleration be over here? We know we can quantify acceleration as a change in velocity, meaning final velocity minus initial velocity, divided by the time interval t. In our case, we can just plug in our numbers, 50 minus 10 divided by 40. That will give us exactly 1 meters per second square, which means for every 1 second, Tufi speeds up by about 1 meters per second. That's precisely what a 1 meters per second square acceleration means. Great. Now let's suppose Tufi continues to move with the same speed of 50 meters per second. Let's in fact suppose we're looking at his car from above. That's his car right here. And he's moving with the same speed of 50 meters per second and maintains it. And suppose that instead of moving in a straight line, he encounters a turn and so changes his direction like this. Now the question we have isn't numerical over here. It's quite straightforward. In fact, it's a yes or no question. Is Tufi accelerating here? Yes or no? Give this video a pause and think about this. Do you think Tufi is indeed accelerating? If so, why do you think so? And if you say he's not, then why is that so? You're done wondering about it? Well, let's see this for ourselves. To know whether or not Tufi is accelerating here, we have to remind ourselves of what acceleration is. Not just to its limit of just the equation. We know what the equation is. It's just v minus u over t. We already used that. But it's far more important to bring up the definition of acceleration, which I'll bring up right here. That acceleration is the rate of change of velocity, which means ultimately, if velocity is changing, there will definitely be some acceleration involved. Now comes the next question. When is it that we even encounter a change of velocity to begin with? Well, for this, one very obvious answer that we might think of is that, okay, velocity will change when its value changes, which is precisely the scenario we saw previously. We saw Tufi changing his value of velocity from 10 meters per second to 50 meters per second in some time duration. But this time the direction wasn't changing. But we have to remind ourselves, and in fact I'll write it here, that velocity is a vector. Since it's a vector, it has magnitude or a numerical value and a direction. So a change in velocity doesn't just entail the scenario where its magnitude or its numerical value changes, but it also is possible when there's a change in direction. When its direction changes. In this case, we don't see the magnitude of Tufi's car change, but we do see his direction change. He's going from towards the east and then changes his direction to point towards the south. Clearly, there's an obvious change in direction that's happening, meaning in the time where there is a change in direction happening, there is definitely acceleration happening. So the answer to this question is yes. Why? Because there is a change in direction involved. So why is Tufi accelerating? Because Tufi's car's velocity changes direction as he turns. So all of this is to just kind of understand that when it comes to knowing whether or not an object accelerates, we must take into account both possibilities. We have to remind ourselves that since velocity is a vector, vectors don't just change when their numerical value changes, but they also change when their direction also changes. So in this case, where there's a change in direction happening and no change in value, that still counts as a change in velocity. And so in this turning scenario, Tufi is indeed accelerating. So I hope you were able to better understand how you can apply our basic fundamental concepts into different scenarios. Hopefully, with a better understanding of these kinds of questions, you'll be able to deal with theoretical questions and conceptual questions that we encounter in past papers far more easily. And that will come later on as we proceed with these lecture series. Thank you.